All right, mixtures. We normally say that mixtures are a combination of compounds by physical means in which the constituents retain its physical properties and composition. For example, sugar is a compound, water is a compound. If you combine them, that's mixture. Or we can say that mixture is defined as the combination of two or more constituents in which every substance retains its own composition and properties. So we can make a lot of mixture. We can mix salts and sugar. We can mix salt and sugar. We can mix sand and salt. Notice that all this kind of mixture is like solid to solid. So we have liquid to liquid, we have solid to gas, we have gas to solid, and the rest. All these are all types of mixtures. But under this mixture, I want you to get that there is a basic type, and the basic types are what we call heterogeneous mixture, and this is mixture that is more than one phase, or mixture that is not uniformly combined. Then we have what we call homogeneous mixture, and we say that every homogeneous mixture is a mixture that is in one phase, so they are properly combined. And another name for homogeneous mixture is what we call solutions or solution. So we say that a solution is a mixture that is in uniform combination, or that is in one phase. Now, for the concentration of a solution, let's focus on homogeneous solution, and the solution we'll be dealing with is liquid in liquid solution. So for homogeneous solution, to get the concentration, or what we call measurement of a solution, to get the concentration of a solution, we normally do it by what we call percentage composition. And to get this percentage composition, we can check it by a number of ways. We can check it using weights per weight, and this is the number of solutes contained in 100 gram of solvent. So number of solutes contained in 100 gram of solvent, number of solutes in 100 gram of solvent. So that means solute per solvent. Then we have volume per volume, and we say that this is the volume of solutes, V solutes per V solution. Then we have gram per dm cube. So this one is like density. So this is mass over volume. So these are ways to measure solution. Then we have molarity. And molarity, we've done this in class. Molarity is simply when you're talking about mole, that is the number of mole all over, that is to the ratio, or the ratio of mole to kilogram of solvent. Take note that is solvent you are dealing with. Always take note. So if you don't use kilogram of solvent, you say 1000 grams of solvent. Then we have what we call molarity. You need to know this one. So all these things still fall under our class when we did concentration. I would say that this one has to do with moles of a solute to the volume of solution. So these are ways we measure the concentration of a solution. And we know that concentration simply means the proportion of solutes in a solvent. Do you understand? So the proportion of solutes in a solvent gives you concentration. Or you say the amount of a solute, or amount of something, or amount of solution, or amount of solutes and solvents in a solute that make a solution is known as concentration. So now remember that another way to define solution is simply the addition of solutes to solvents. So solute plus solvent gives you solution. So this one, this solute means the one that is in lesser quantity, or you say the one that gets dissolved. So that quantity, or the substance, that substance that gets dissolved is known as solute, while that substance that is in larger quantity, or the substance doing the dissolving, that substance that is dissolving this other substance, or that is doing the dissolving, is known as the solvent. And we have things like water, glucose, mercury, a lot of them, ethanol as solvents. Now we know that glucose is a non-volatile solvent. Water is a volatile solvent, which means glucose does not evaporate readily, while water evaporates readily. So if I know this, so that is for introduction aspect of solute and solvent and solution. So in our next class, what we are going to be treating is what we call ideal solution. Ideal solution. Ideal solution. And this ideal solution is simply a solution whereby there is no intermolecular forces. So it's more like an imaginary should I say understanding. Ideal solution, more like an imaginary understanding, where we say yes, we know that every solution has an intermolecular forces, but that is in a real world. Okay, every solution has an intermolecular force, but in ideal we say everything being perfect, let there be no intermolecular forces, so that the minute I heat this up, it starts boiling. There is no delay. So that is what the idea of ideal solution gives us. So if we know this, we now say that if this ideal solution exists, if we take it to exist, we now make use of what we call Raoult's law. And this law gives us the account that vapor pressure, you know that since there is no intermolecular forces, if I heat it, it starts boiling. What makes it take long to boil is the surface tension, trying to overcome all those forces. So now if it's an ideal solution, it should boil immediately. So there is a law by Raoult's law, and this Raoult's law is one of the chemists that played so much with vapor pressure. And he said that the vapor pressure of a solution, let's say this is PA for solution, is directly proportional to its mole fraction. And if this is the case, he's saying that at equality there will be a proportionality constant, which is now going to be vapor pressure of a solution will be equals to Kxa, and this K is equals to the vapor pressure, that is the vapor pressure of the pure solvent, yes. So let's say this is now, or we say if you don't use pure solvent, you say it is that vapor pressure that happens at a particular temperature, that one that happens to a liquid or a solvent at a particular temperature. So it is always constant. For example, see what I mean. If I mix water and glucose, the vapor pressure that it will have might be extra or lesser, compared to what vapor pressure water will have naturally on its own. So this one is due to the solution. While whatever I'm having in the solution, both the solute and the solvent, Each of them, solute and solvent, make up a solution. So in every, even if it's liquid and liquid, every solution has the one that is the solute and the one that is the solvent. So each of them, inside this containing vessel, has its natural vapor pressure that, should I say, that comes on account of what it does on its own naturally before it combines. So whenever it's combined to form a solution, we take account of the vapor pressures of the solutes respectively, and that of the solvent respectively, and it always happens at a particular temperature. Remember, I told you that the vapor pressure of water, is always 100 degrees C, is always at 100 degrees C. So at 100 degrees C, water should have a vapor pressure of 760 millimeter mercury. So that is the vapor pressure of water naturally. So when you replace it, is a constant. So when you replace it with this proportionality constant, you now have what you get in most textbooks as Raoult's law, which gives account of vapor pressure of a solution to be equal to the product of the pure vapor pressure multiplied by the mole fraction. So once you're talking about uh what's it called, anything ideal solution or vapor pressure, we always make use of this. So we can say where Pa equals to vapor pressure of solution, vapor pressure of solute or solvents due to its presence in a solution. Why Pa raised to power is called maximum vapor pressure, or you call it pure vapor pressure. Sometimes students ask me, how do I know the difference between the pure vapor pressure and that of the solution? How you know is that if a question tells you the vapor pressure of pure water, know that they are talking about vapor pressure of at that temperature, the pure vapor pressure. Or they tell you at so degree the vapor pressure of water is this, know that they are talking about this one, the pure vapor pressure. But if they tell you a solution of glucose and water did this, then they now tell you the vapor pressure of water is this, know that they are talking about this one. So the vapor pressure due to solution is that one that you have on the left hand side, while the pure vapor pressure or vapor pressure happening at a particular temperature is the one on the right hand side. So then XA is equals to mole fraction. So if I know this, by the knowledge of this, I can go ahead to expatiate on what mole fraction is. We know that from the word mole, in fact, anytime you hear fraction, just know that another name for fraction is composition. It's more like telling you, get the lowest bit. So it's just like if I'm asked mass fraction, or I'm asked mass percent, all I need to do is to get the mass fraction, then multiply by 100. So in a case where I'm asked mole fraction, in fact, once I see any question under vapor pressure, they tell me vapor pressure of anything, and I see gram in that question, I just need to go and convert it to moles. And when I finish converting to moles, I now apply mole fraction. So to get mole fraction is simply to do, let's say for example, I have solution. Let's say I have solution that contains A as the solute and B as the solvent. So what mole fraction is all about is simply get the mole of A, divide it by the mole of A plus the mole of B. And you know that this is what we call total mole. So another way to say it is that mole fraction is simply mole of constituents divided by total mole of the compound or of the mixture. So mole of constituent divided by total mole of the mixture of the solution is what you know as mole fraction. So this will now be mole A divided by total mole. So this is the same thing, because A plus B gives you this. So that means mole fraction of A is going to be this. That means to get mole fraction of B, mole fraction of B, which we write, we represent this mole fraction with XB. This one will be the same thing as saying XA. That is how we represent it here. So this will simply be the same thing as saying mole of B all over mole of mole A plus mole B, which is the same thing as saying mole of constituent, which is B, all over N total. And N total is the same thing as saying total mole. So if I know this, I believe what is remaining now is to solve questions. So, and also in some cases you can be given to plot a graph of vapor pressure. Know that and against mole fraction. So the idea of this is that, remember that the law, Raoult's law, first says that as vapor pressure is increasing, mole fraction should be increasing. So the idea is that if this is 0 and this is 1, 2, 3, notice that mole fraction is increasing. So this one, as it's increasing 1, 2, 3, so on, it should be in such a way that this 3 equals this one. Are you seeing it? So if this is benzene, vapor pressure of benzene should be this way. It should be in this way. So that as it's going to 2, this one is also going to 2. They are moving this way. So if, for example, I have methyl benzene, this will be in such a way that everything I do will always equal to 1 for the mole fraction. So I'm not supposed to use 3. So I should use, for example, let's say I used 0, 0.25, 0.5, 0.75, that is 0.25, 0.5, 0.75. So whatever mole fractions I have, the solute and the solvent, it should always equal to 1. It should always equals to 1. So this should give me 1 somewhere here. So that means I will have, when I have 1 here, I should have 0 for the other compound. Let's say I'm doing, I guess, with methyl benzene. Then here I should have 0.25. 0.75 plus 0.25 gives me 1. Then I have 0.5. Then I have here 0.75. Then I have here 1. So if I'm having it with this is solute and solvent, I should make it in such a way that the both equals to 1. The same thing on this side, so that when I'm plotting for this one, it should be moving in this way. It's this way. So I have a graph class already plotted for this. You check the video on mole fraction of benzene against vapor pressure against mole fraction of benzene and methyl benzene. So with that said, another thing I want to prove before leaving here is that since we know that Raoult's law gives us the account that PA, vapor pressure of solution, is directly proportional to pure vapor pressure and mole fraction. And that's the first principle. The second principle is that XA plus XB should equal to 1. So if I know this, that means that XA is the same thing as saying is equals to 1 minus XB. The same thing, that means XB is equals to 1 minus XA. So I can carry any of these and put inside equation 1. So these are the two major principles of Raoult's law. So of ideal solution actually. So two important principles, two major principles. So let's say I put any of these for equation 1. So I will now have PA, is equals to PA degree Know that I can also have vapor pressure of B constituent, but I'm using that of vapor pressure of A. Then where I see A now, A is equals to, where I see AC, A is equals to 1 minus XB. That's what A is equals to. So I replace it. So this is going to give me, there's so much air here, that's the problem. So this is going to give me PA is equals to PA naught, that is the way we call it in class, minus PA naught XB. Now notice that I can carry everything here and come over this side, because remember we are trying to make what's it called? We're trying to make x mole fraction subject of the formula. So I will now have that if this come over here, let this one come over here. I want to do it this way so that I can get what I call lowering of vapor pressure. So this coming over becomes positive. PA naught XB is equals to PA naught is already here minus PA. This particular thing you see here, when we are doing colligative property, anytime we have pure vapor pressure minus vapor pressure of a solute, or the normal vapor pressure due to the solution, this is what we call lowering of vapor pressure. Now notice that the minute I get it here, I can say to make x be mole fraction subject of the formula, this will now become XB. Okay, let's just do it this way. PA naught XB is equals to PA naught minus PA. Divide both sides by PA naught. This PA naught, this will cancel this PA naught. So you see that at this point you are having XB, mole fraction of solvents or mole fraction of constituents B, is equals to PA naught minus PA all over PA naught. And what you have here is what we call relative lowering of vapor pressure, and it's a colligative property. It's one of the colligative properties, lowering of vapor pressure. So this is what we call relative lowering of vapor pressure. So even if I don't use A, I just use P naught and P, you still get, and just use X to notice that this is the second X. So it's the same thing as the answer to that your question, your assignment question. So if I have this, I will now have mole fraction is the same thing as saying N, in this case mole fraction of B is NB all over NA plus NB is equals to PA naught minus PA all over PA naught. So notice that this NB here, we normally say that its effect is not much when added. So you see some textbook leaving it as NB all over NA is equals to PA naught minus PA all over PA naught. So this is proved. We can use the second principle. We can use this second principle, this one, by making it any of this and substituting for whatever you have here to get relative lowering of vapor pressure. So in our next class, we'll solve questions on this to make you understand better. Please subscribe to the channel, like, share.